In structural engineering, the term linear load refers to a load that is distributed uniformly along the length of a structural member. This means that the load is applied evenly across the entire span of the structural element, rather than being concentrated at a single point or in a small area. Linear loads are a common type of loading scenario encountered in various engineering applications. They are essential to understand for accurate structural analysis and design. The concept of a linear load is fundamental to ensuring the safety and stability of structures. Understanding linear loads involves several key aspects. Firstly, the definition and characteristics of linear loads. A linear load, also known as a uniformly distributed load, or UDL, is characterized by its constant magnitude per unit length. This means that for every increment of length along the structural member, the same amount of load is applied. This uniformity simplifies the analysis and design process compared to concentrated loads, which act at specific points. Secondly, consider the units of measurement. Linear loads are typically measured in units of force per unit length, such as newtons per meter, or N/m in the metric system, or pounds per foot, or lb/ft in the imperial system. The units reflect the distributed nature of the load and are crucial for accurate calculations. Thirdly, examples of linear loads in real-world scenarios. Linear loads are prevalent in numerous engineering applications. Common examples include the weight of a wall supported by a beam, the load of snow distributed across a roof, or the pressure exerted by water on a dam. In the case of a wall, the weight of the masonry or other construction material is evenly distributed along the length of the supporting beam, creating a linear load. For a roof, the weight of accumulated snow is generally uniform across the surface, resulting in a linear load on the supporting structure. When designing a dam, the water pressure increases with depth, but over a small section can be approximated as a linear load acting horizontally. Fourthly, analyzing structures subjected to linear loads. The analysis of structures under linear loads involves determining the internal forces and moments within the structural member. These internal forces and moments are essential for assessing the member's capacity to resist the applied load without failure. The analysis typically involves calculating shear forces, bending moments, and deflections along the length of the member. Shear force represents the internal force acting perpendicular to the longitudinal axis of the member, while bending moment represents the internal moment that causes the member to bend. Deflection refers to the displacement of the member under the applied load. Fifthly, understanding the methods of calculation. Several methods are available for calculating the internal forces and moments in structures subjected to linear loads. One common approach is to use static equilibrium equations. These equations express the conditions for translational and rotational equilibrium, ensuring that the structure remains stationary under the applied loads. Another approach is to use structural analysis software, which can automate the calculations and provide detailed results. These software tools utilize numerical methods such as the finite element method to analyze complex structures with various loading conditions. Sixthly, consider the impact on structural design. The presence of linear loads significantly influences the design of structural members. Engineers must consider the magnitude and distribution of the load when selecting appropriate materials and dimensions for the member. The design must ensure that the member can withstand the internal forces and moments generated by the linear load without exceeding allowable stress limits or experiencing excessive deflections. Factors such as the material's yield strength, modulus of elasticity, and cross-sectional properties play a crucial role in determining the member's load carrying capacity. Seventhly, the support conditions and their effects. The support conditions of a structural member also play a critical role in its response to linear loads. Different types of supports, such as pin supports, fixed supports, and roller supports, impose different constraints on the member's movement and rotation. These constraints affect the distribution of internal forces and moments within the member. For example, a fixed support provides both translational and rotational restraint, resulting in higher bending moments near the support compared to a pin support, which only provides translational restraint. Eighthly, discuss the concept of equivalent concentrated load. In some cases, it may be convenient to replace a linear load with an equivalent concentrated load for simplified analysis. The equivalent concentrated load is a single force that produces the same external effects, such as reactions at the supports, as the original linear load. The magnitude of the equivalent concentrated load is equal to the total magnitude of the linear load, and its location is at the centroid of the linear load distribution. However, it's important to note that using an equivalent concentrated load may not accurately capture the internal forces and moments within the member, especially for detailed stress analysis. Ninthly, safety factors in design codes are important. In practice, engineers incorporate safety factors and adhere to established design codes to ensure the structural integrity and safety of structures subjected to linear loads. Safety factors are multipliers applied to the calculated loads or material strengths to account for uncertainties in the analysis, design, and construction processes. Design codes, such as those published by the American Institute of Steel Construction, or AISC, and the American Concrete Institute, or ASCI, provide specific guidelines and requirements for the design of various structural elements, including those subjected to linear loads. These codes incorporate years of research and practical experience to ensure that structures are designed to meet minimum safety standards. Tenthly, advanced considerations. Beyond the basic principles, there are several advanced considerations related to linear loads that engineers may encounter in complex projects. These include non-uniform linear loads, where the load intensity varies along the length of the member, and dynamic linear loads, where the load varies with time. Analyzing structures subjected to these types of loads requires more sophisticated techniques such as finite element analysis and dynamic analysis. In summary, a linear load is a uniformly distributed load along the length of a structural member. It is measured in force per unit length, like newtons per meter or pounds per foot. Common examples include the weight of a wall on a beam or snow on a roof. Analyzing these loads involves calculating shear forces, bending moments, and deflections. Static equilibrium equations and structural analysis software are used. Supports like pinned or fixed ends affect the distribution of these forces. Engineers use safety factors and design codes such as those from AISC and ACI to ensure structural integrity. More complex scenarios involve non-uniform or dynamic linear loads requiring advanced analytical techniques.